Hello everybody. For this video, we're going to talk about section 3.1, which is on exponential functions. What's really interesting about this particular section is that this is just serve as a definition for what an exponential function really is even talking about. And we kind of have an idea what exponential expression looks like, but at a very specific level. So if n is a positive numbers, then we can talk about any sort of a to the nth power, and this is just how many a's multiply with itself. So this is just a times a times a dot dot dot, and altogether there's n many a's, right? N times. So this is a very rudimentary way of defining exponents, and it's useful for a really long time. And then we talk about negative exponents. But the way we make sense of this is simply by relating that back into a to the positive power of n. Instead, here we have to use 1 over a to the power of n. And of course, a to the power of n is defined the same way as before, so a times a times a, n different times. Well, the last thing here is rational exponents, right? If we take a fraction, what does a to the p over q mean? Well, this means the q's root of a to the p power. Okay, we still basically want to treat this fraction as a integer over another integer. So the integer on top is going to be the exponent, right, as we were working on all before, but the integer on the bottom becomes the root, which is essentially the opposite of this uh, this exponent. Okay, so that's how we've been defining exponents so far. We have positive integer, we have negative integer, we have rational numbers. Here's where the problem begins. We don't have a way to really define it up until this point, up until this section, that is, anything that's not rational. Anything that's not rational. So a lot of numbers are irrational, aka not rational. In fact, there's a lot more of these irrational numbers than rational ones. So to create a function, we have to be able to handle numbers that are irrational, or at least, this is the only way for us to talk about a continuous function. So what we need to do here is to define how we can approach a irrational exponent. So for example, what about the expression of 2 to the power pi? What does that even mean? Well, the way we're going to tackle this is by the idea of limits. So here we know that pi is equal to 3.141592, blah, blah, blah. I'm sure this is the number of digits that everybody remember to. What we can do here is we can approach pi by using a series of, or by using a bunch of terms that are just using a finite number of decimals of pi. So for example, we know that pi obviously is between 3 and 4. Pretty easy to see there. But then we can add more digits, while pi is also between 3.1 and then 3.2. Okay, because 3.14, right? Going into the third decimal place, we know that pi is between 3.14 and 3.15 because it's 3.141. Going on 3.141, 3.142, because the next one is 3.1415, right? So all of these allow me to bound pi by two numbers that are irrational, that are rational, right? Because you can easily write these into fractions, okay? And if we keep going, if we do this forever, if we find this limit of this process, on the left-hand side, it approaches to pi from the left. All of these numbers are less than the number pi, while all the numbers here are approaching pi from the right. Okay. So what we really have here is we have a way to express pi as almost kind of a squeeze theorem effect, where we take two sides of the limit and squeeze them from the left and to the right, and we can define pi essentially as a squeezed limit, okay, as a squeezed limit. Well, the good news about limits is limit behave very nicely over continuous functions. Okay, what we can do is we can play the same exact game. So I don't know what 2 pi is, but I know for sure is less than 2 pi cubed, and sorry, it's greater than 2 pi cubed and less than 2 pi to the fourth, 2 to the fourth. Similarly, I can move one more digit, right? Again, I don't know what 2 pi is. I know it's going to be bigger than 2 to the 3.1 power, and then it's less than 2 to the 3.2 power. Okay, because all of these are rational exponents, which these are defined using this thing here. Okay, so if we go ahead and play that same exact game as before, we notice that all of the stuff on the left are going to be less than 2 pi. So it is approaching 2 pi from the left. On the other hand, all of the stuff here are going to be greater than 2 pi. So this approaches to 2 pi from the right. And we're going to use both sides to define exactly the limit as the 2 to the power of pi. Again, in the same fashion as we see before in the squeeze theorem fashion. Now, this is the definition. Now, you're definitely not going to be using this definition forever, just because each one of these is a series of infinite limits. Okay, but this is how we're going to formally define the exponent of an irrational number. Here we go. Let A be any positive real number. Technically, is any positive real numbers, but you typically don't work with number A equals to 1. Then for any real number x, any real number x, irrational, rational, fraction, integers, whatever, a to the power of x is equal to the limit as r approaches to x, a to the power of r, but then the important restriction here is we have to force r to be rational numbers. So this is a little bit different than the limit from chapter 1. The limit in chapter 1 are always going to be limits that work with real numbers, are always going to be limits that essentially have no gap in the middle. But here, we are working with specifically rational numbers, aka fractions. Now, in some sense, there's a gap. There's now a little bit of a gap for irrational numbers, right? Just because you're missing a whole bunch of irrational numbers that kind of fills in the gap. But it turns out there is a very important, very strong theorem in terms of analysis where it says between any numbers, any two numbers, real, fractions, right, irrational numbers, whole numbers, there exists a fraction in it. Okay, so while there is some gap, the gaps are because rational numbers are what we call dense, the gaps are negligible. So this right here is the very definition of the a to the power of x for any real numbers. But of course, if we're talking about rational numbers or integers, then we don't need this definition. It is true, but we don't need it. We specifically are using this definition for any irrational number, like pi, like square root of 2, for example. These are all irrational numbers. The number that has decimal places goes on forever. Okay, so this is a kind of important definition that we have to kind of keep in mind, just because otherwise you have no way of defining the exponent of a irrational number. But once we have this, then the rest is pretty straightforward. The exponential functions, right, now that we have all of the possible values, is basically something that looks like this. Is just mainly separated by two categories. Again, you typically don't work with the base equaling to 1, but the base has to be positive, and one category is that the a, right, the base, exponential base, is greater than 1, and the other one is between 0 and 1, right? Again, it has to be positive. So let's talk about these real quickly here. So for numbers that are bigger than 1, right? So for example, 2x, oops, 2x, 5x, right? 1.7x, about 1.001x, right? These are all numbers greater than 1. All of their functions look very similar to this. Okay, very similar to this. The important part is that they're always going to cross here, which is the 1 comma 0. Sorry, 0 comma 1. Because any exponential functions, when you plug in 0, you're going to get 1. Okay, everything else though looks basically exactly like this shape. Now, when you hear people say stuff like, oh, it's increasing exponentially, this is kind of what they're talking about. Okay, we see that at the early stage, it's actually very kind of, kind of flat almost, right? But then it just shots up. Okay, so exponential increases very, very fast for bases that are greater than 1. Okay, we'll talk about this increasing speed in the future sections, but for now, this is what we have. The domain for exponential functions are always going to be negative infinity to infinity. One of the reasons why we really like this kind of function is because they have infinite domain. The range, however, is always going to be from 0 to infinity. In other words, you cannot obtain 0. Exponential functions are not equal to 0 in the real numbers, right? In the real number world, that's not going to happen. And it's never going to be negative, right? We're talking about basic exponential functions that look like this, right? Obviously, you can make things into negative by multiplying by negative on the, in the front. So something like negative 2 to the power of x. This is definitely going to reach negative, but this is right here is a modification, right? A function transformation to the basic exponential function. The two things that you really do need to remember, though, is because of this structure, on the left-hand side, it's going to be more and more flat, but on the right-hand side, it shoots up, right, very, very fast. So as x approaches to negative infinity, a to the power of x is equal to 0 for anything a greater than 1. On the other hand, as x goes to infinity, a to the power of x, while it shots up to the right-hand side, this is going to give you infinity. Okay? On the other hand, if you're in between 0 and 1, for example, 1/2 to the power of x, 0.7 to the power of x, 0.999 to the power of x, right? You can get as close to 1 as you want, but as long as it's not 1, then it basically is going to follow something to this effect. Okay, kind of going down. In this case, the domain and range is exactly the same. The domain and range is exactly the same because what ends up happening here is this is just a mirror reflection of the previous case, right? This is a reflection about the y-axis. And we can see that too because it crosses the point 0, 1, just as before, and it's basically symmetric from left to right. Okay, what that means here is that the limits are flipped. So as x approaches to negative infinity, we're going this way, but then the graph is shooting up very, very fast. On the other hand, if x goes to infinity, we're going this way, we can see that this is becoming flatter and flatter and flatter until it approaches to 0. So as x goes to infinity, then this thing goes to 0. And the way you can visualize both of these, by the way, if you don't want to remember things like, I don't, you can kind of play around with this just by using, the stuff like 1/2, right? If you do 1/2 to the first power, that's obviously 1/2. But if you do this to the second power, 1/4, 1/2 to the third power is 1/8. 1/2 to the fourth power is 1/16. The point here is, as the number of the exponent increase, guess what? The function decrease, right? And then this is always going to be positive, but it's going to get smaller and smaller and smaller just because you're going to have bigger and bigger denominator. So you're going to approach 0. Versus the other case, right? Again, just maybe think about 2. So 2 to the first power is 2, but 2 to the second power is 4. 2 to the third power is 8, and 2 to the fourth power is 16. Hopefully you see where I'm going with this, right? If the power becomes really, really big, then the number just increases without bound, right? So it's going to infinity. I mean, once you remember, once you play around with these, it's easier to remember the other one. Okay, just kind of the other one goes to 0. Okay, so you can always kind of test this one out if you want to think of it that way. Well, let's play around with this. Here we go. The first one, limit as x goes to infinity, 4 to the power of x. Here, 4 is clearly greater than 1. And again, if we think about plugging in bigger and bigger exponents, right? 4 to the first power is 4, 4 to the second power is 16, 4 to the third power is 64. This is going to increase without a bound. So then the limit is just going to infinity. Similarly, for the next one, the limit as x goes to infinity, but this time is 0.9 to the power of x. And 0.9 is clearly less than 1. So the more power you take, the smaller you're going to get. For example, 0.9 to the second power is 0.81. 0.9 to the third power is 0.729, right? It's just going to get smaller and smaller in terms of decimal. So this is equal to 0. Okay, so you follow the cases from before. Actually, I want to use the same color scheme. Oops. This is what I should put. Now, if you're working with this mixture of limits, this is something that you kind of have to invoke something from before. The way we want to do this is, I don't want you to think about just plugging in x equals to 0 from the left. First of all, that will be a silly way of plugging in anything that is directional. Okay, the way I want you to think about this is to kind of do a substitution, if you will. So if we let, say, t equals to 1/x, okay, then what we notice is, as x approaches to 0 from the left, t is approaching to what? Well, the limit as x approaches to 0 from the left of 1/x, well, we know that limit. This, maybe I'll remind you of what this looks like here. The 1/x function, right, looks like this. So as x approaches to 0 from the left, I'm actually going this way. So t is going to approach negative infinity. Now what we can do is to make a substitution. So this whole limit, right, I want to get rid of everything in terms of x. I want to write everything in terms of t. So the limit as x approaches to 0 from the left is the same as t approaches to negative infinity. And then 3, 1/x just becomes t. You see, now we're working with 3 to the power of t. 3 is clearly bigger than 1. So this actually falls under the, this case right here. So then as x, or in this case, t goes to negative infinity, our limit is equal to 0. So this limit is equal to 0. Okay, so that's the formal way, or at least a more formal way of writing this. We want to do a substitution so we can talk about the limit outside of performing the limit here directly. That's the whole point of this portion of the work. Okay. So here is something that I want to introduce. Finally, we want to introduce this number e. We've been working with this for quite a while now, but this is formally called the Euler's number, e, and this is actually defined in this very, very particular way. We will be able to work with this eventually in the future, but for now, this is just a definition. This is just the limit as x approaches to infinity, 1 plus x to the power of 1 over x. Very specific type of limit, and we can't even evaluate the limit here just yet, just because this limit is a very specific structure where you have a variable in the base and a variable in the exponent. So this is not really a composition in any of the standard way. Okay? We'll talk about exactly how to deal with this kind of limit in the future section. But for now, this is the most formal definition of the number e. The decimal value of the number e, though, is really, really nice. It's just going to be these right here. E is approximately 2.718281828. If you just talk about the first 9 digits, you might even think it's going to repeat, but the rest is just kind of going down the hill from there, right? So 45904523536, and etc. No one remembered this one as much as people remembers pi, I guess, but it's nice to kind of know what this number is all about. What's really weird about this number, though, is that the common, I guess, the common abbreviation of this number, or sorry, approximation of this number, uses e approximately equals to 2.71, which is kind of silly because if you think about rounding, right, if you round to the second decimal place, then you need the third, then this will probably be round to 2.72. I'm actually not sure about the reasoning behind this, so if you can find out, you let me know. But a little bit of background story about this, you can take a read that if you want. But what's really interesting here is this thing is often thought about as a number that's discovered not by mathematicians first, but by accountants when they're thinking about finance, when they're thinking about compound interest. It just shows you that when money is involved, anybody can be mathematicians. Anyway, this is finally formalized by the great mathematician Euler, and he did many, many things, many things. But what's funny here is that he claimed that the E stands for exponential, not from his name. So I'll let you be the judge of that. Sneaky Euler put himself down in history forever. I guess that's one way to do it. Okay. I'm sure you are familiar with this already. We've been working with stuff very similar to this. So I just want to remind you some property of exponential expressions. The only thing different is that now x and y are now functions, variables that can take on irrational numbers, right? Whereas previously you shouldn't be working with irrational numbers. But honestly, we've been working with irrational numbers anyways. So here we go. But another one that's really important that will be useful for us in the next section is this property, which is the one-to-one property. This is a big one. The one-to-one property allows you to kind of drop the, allows you to drop the exponential base and claim that the exponent themselves are equal. Now, this is not obvious because this clearly does not work in the polynomial world, right? You cannot say that x squared equals to y squared, therefore x and y are equal. You cannot drop the exponential power. For example, -1 squared is equal to 1 squared, but you can't drop the exponent and say -1 is equal to 1, right? So this does not work. And we know that the square function is not one-to-one, so this much should be somewhat obvious. Okay, so one-to-one property turns out to be very important, and we can leverage that to solve some basic exponential equations. Let's take a look at this. So the idea here is I want to leverage the one-to-one property. That means what I need to do here is to bring both sides to a power of the same base. On the left-hand side is everything to the power of 3. So I want to somehow write the stuff at the right as power of 3 as well. And the way I can do that is, first of all, copy and paste the left-hand side. I can work with 81, right? If I can't do 1 over 81 right away, I can work with 81. So 81, we know, is 3 to the 4th power, right? Because 81 is 9 times 9, and 9 is 3 times 3. So if you prime factor it, you will have 3 to the 4th power. What I can do then is to leverage the property of exponent. I can move this exponent on the denominator to the numerator by treating it with a negative exponent, right? That's essentially this property right here. And now the one-to-one property kicks in because both sides are now raised as powers of 3. So then the power of the 3 drop. We have simply x plus 2 equals to -4. Here, just subtract 2 on both sides. We get x equals to -6. Very easy property to work with. Okay. Moving on to this one. This one's slightly a bit more complicated. Again, same idea. I want to raise both sides as the same exponent. So I want base 5, right? Exponent to the power of 5 here. 125, same idea. I can do 125. I can divide that by 5, and then I'll have a 25. And then take the 25 and break it down into 5 times 5. So altogether, 125 is 5 cubed. The problem here, though, on the left-hand side is that I have 2 powers of 5 multiplied together. So I can't just drop the powers of 5 right away. What I have to do is to combine these 2 powers of 5 together. And that, I have to use this property. Same base, different power, we just simply add the power together. So here, this is going to be 5 to the power of 4x plus 1 plus 2x minus 7. Now I have both sides as powers of 5. I can apply the one-to-one property, and the 5 drops. We have 4x plus 1 plus 2x minus 7 equals to 3. And then the rest is child's play at this point. Combine the powers of the like term of x, we have 6x. Combine the numbers together, we have minus 6 equals to 3 plus 6 on both sides. 6x equals to 9. And finally, divide 6 on both sides. X equals to 9 over 6. or if you simplify top and bottom, divide top and bottom by 3, you get 3 over 2. Okay, so this is really just a kind of a too simple application to the properties that we mentioned above, especially the one-to-one property. This is really important for the next section, and of course, this is how we basically are going to define the inverse function of exponential functions, which you guys all know are logarithm functions, but we'll see that in the next section. That's it for this video. See you guys in the next one.